Unless anyone objects, or if you want to object, you can object by email if you don't want to object verbally. All right, so let me say what are the prerequisites for this course. And this is something that's relevant not just to the people at UGA. So what I'm going to assume is some knowledge of homological algebra. And in particular, I'm going to assume you at least have some familiarity with abelian categories. You don't really have to know a huge amount about them. You have to know, like, they're kind of like categories of modules. You have to be pretty comfortable with derived functors. And you at least should have seen in your life a spectral sequence. I mean, if you haven't seen every single one of these things, that's okay. You can come to my office hours, which I'll announce the time probably via email and on the Discord in a couple days. And we can go over some of that. Okay, so you should also know what a sheaf is. And you should have some familiarity with sheaf cohomology. Okay, and you should know what a scheme is. So in particular, almost all of this is covered in Hartshorne chapters 2 and 3. So if you've gone through Hartshorne chapters 2 and 3, you have the prerequisites for this course, more or less. So if you're missing some of that, that's okay. Come talk to me and we'll see if we can work it out. There's a Discord where we can discuss things, and you can ask your friends and co-classmates there. And if you haven't joined the Discord, please do. I'm gonna post a link in chat right now. So please join the Discord, and I'll usually make like course announcements there, and also there will be some discussion of the course there. And there's like a lounge, which I will try not to look at too much, where you can also just like chat and be friends with each other as if this was a class in a normal time. So please join the Discord, and also this Zoom with your full name. Okay, are there any questions about the Discord or about the prerequisites for this course? So again, feel free to just raise your hand, or raise your hand using the buttons under the list of participants, or just unmute yourself to ask. All right. And if not, then we'll just go ahead with the mathematics. So let me start with maybe the basic question. So this course is about Etale cohomology and the Weil conjectures. So what is Etale cohomology?
So before that, can you give us a rough outline of the topics you plan to cover?
Oh, sure. Yeah, that's a great idea. In fact, that was what I was supposed to do next, and then I skipped that part of my notes. Okay, so what are the goals of this course? So goal 1 is to cover the basics of Etale cohomology. So for example, I'm going to tell you what an automorphism is. Hopefully you've seen that before. I'll tell you about Grothendieck topologies. Which are a generalization of the notion of a topological space, and in particular the Etale topology. Then we'll more or less for free, once we have that, we'll have a definition of Etale cohomology. And then the basic theorems. We'll also be computing it in some cases. We have to know some things. So the main computation in this course will be Etale cohomology of curves, which is surprisingly non-trivial. And then there will be some comparison theorems to usual singular cohomology. Okay, so that'll be the first half of the course, and this will more or less follow Milne. So Milne has 2 books on Etale cohomology, and we're going to be loosely following lectures on Etale cohomology. He also has a book that's just called Etale cohomology, which covers a lot more, and it's very good. And that's something you should also consider using as a reference for the course. And then I'm also going to supplement this with stuff from Freitag Kiel. And yeah. Okay, so then once we do that, we're going to prove the Weil conjectures. And if there's time, I actually want to give more than one proof of the Weil conjectures. So this is going to be kind of the second half of the course, where we're going to prove the Riemann hypothesis for varieties over finite fields. It's like one of the greatest like mathematical accomplishments of the 20th century. And then if there's time, we'll do some more advanced topics. And that really depends in part on what you all want to see. For example, we may cover Weil2, which is a strengthening of the Riemann hypothesis. That's actually what you end up using in real life when you use the Weil conjectures most of the time. We might cover some topics like formality of algebraic varieties, which is some kind of special topological features that algebraic varieties have that general topological spaces don't, which follow from the Weil conjectures. And then maybe we'll cover some other topics, depending on how things go. Like for example, well, there'll be some monodromy stuff that shows up in part 2, but we might cover that more thoroughly. So for example, one useful reference we will probably use is Katz's Arizona Winter School Notes, where he kind of sketches one of the 2 or 3 proofs of Weil2. All right. Are there any questions about that?
So I'm not familiar with the stuff a lot, but does this include stuff on Etale Pi1 or no?
Oh yeah. That's probably going to be like the 3rd or 4th lecture. Yeah, so that'll be very crucial. We're not going to be covering like the Anabelian stuff that I like to do with Etale Pi1, but yeah, we'll certainly use it heavily.
And sorry, last question. Will we be mentioning the Brauer group at all?
Yeah. So the Brauer group will actually come up when we do this Etale cohomology of curves stuff. But yeah, so I'm mostly going to focus on Etale cohomology with coefficients and a so-called constructible sheaf, and you'll learn what those words are. But in order to do computations, you have to relate those objects to much more classical things like the Brauer group or coherent cohomology and that kind of thing. So all the sort of classical algebraic geometry that you know how to interpret in terms of H1s and H2s and Pi1s and so on is actually going to show up and be really important. So it may look like a lot of this is kind of formal nonsense, but in fact, in the end, you have to do some work in real life. You know, there's a principle called conservation of work. You can't just make a bunch of definitions and then get what you want for free. And that work is going to be like involve some actual algebraic geometry and some actual arithmetic geometry. So part of the reason I wanted to teach this course is it's an opportunity to talk about all those cool topics. All right. Are there any other questions about the goals of the course? So I do want to say, this is going to be a fairly fast-paced course. If we're going to cover all this stuff, we're not going to prove literally every major theorem in Etale cohomology. I'm going to black box a few things, but like I am going to expect that if you're registered for the course, that you're like doing the work to follow along a little bit. And I know it's like a lot's going on right now. So, if you feel like you're falling behind, talk to me and we'll figure something out. So, I'll have frequent office hours where we can discuss this stuff. All right. Are there any other questions before I move on? Great. All right. So let's talk about what is Etale cohomology. And today's lecture is going to be largely introductory. So I want to kind of draw some analogies to the complex analytic situation, or the space of complex variety, the situation for complex varieties. Then I'm going to introduce the Weil conjectures, and then I'm going to explain how to prove an analog of the Weil conjectures for complex varieties, which, even though it's quite different from the ultimate proof of the Weil conjectures, is sort of really a big motivation for much of what goes on. Okay, so what's the situation? So suppose X is a variety over the complex numbers. By variety, I mean finite type separated integral C scheme, if you'd like. So that's the fancy definition, but you can think just quasi-projective variety, the usual thing that you know and love. So if you take the complex points of this thing, this naturally has the structure of a complex analytic space. For the purposes of this lecture, all that means is that you can give it the Euclidean topology. So that's a much finer topology than the Ruzhevsky topology. And if you have a nice topological space, you can associate to it its singular cohomology groups. Say with Z coefficients. Okay, so what's special about these groups? So they have a few features. So they're finitely generated Z modules, also known as finitely generated abelian groups, right? They have some extra structure. So if you tensor them up to C, that's just the same as taking singular cohomology with C coefficients. These have some extra structure, which I won't get into right now. We'll cover that later. But there's something called a mixed Hod structure on them. And likewise, Etale cohomology is going to have some extra structure on them. And then there's a lot of nice features. So there's cycle classes. So if you have a subvariety of X, you can sometimes associate to it a class in cohomology. Okay, and so forth. Okay, so the goal of Etale cohomology is to do a similar thing for much more general, nice schemes. Okay, so maybe it's worth noting, I mean, some of these properties are actually fairly special to complex varieties. So for example, the fact that cohomology of a complex variety is a finitely generated abelian group, that's not true for a random topological space. Like that's a special feature of complex varieties. And similarly, Etale cohomology will only behave well for reasonably nice schemes. It won't behave well for arbitrary schemes. But so for example, here's the sort of situation. So to X a nice scheme, and I'll be more precise about that in a minute. Nice scheme, you can associate some groups. So HI of X Etale with, for example, Z mod L to the N Z coefficients. Okay. Taking the inverse limit over all N, you get something which is not quite Etale cohomology. It's called L-adic cohomology, and it's a genuinely different object. So you get something with ZL coefficients. So here, this is the L-adic integers. Okay, and then finally, you could tensor that with Q, and you get something with QL coefficients. Okay, and then there's also other things you can do. You can do things like take cohomology with coefficients in a twisted coefficient system. So if you're familiar with singular cohomology with twisted coefficients, there's an analog of that in Etale cohomology, and that'll be really crucial. Okay, and so what kind of schemes are nice schemes? So e.g. you can take X to be spec of the ring of integers of a number field. So that's something you can take cohomology of. You can take X to be a variety over an algebraically closed field. So that'll be the kind of typical situation. So this is most analogous to the situation over C. Or you can also, for example, take X to be a variety over a non-algebraically closed field. Okay, and then things are going to behave very differently. So for example, if you take a variety over an algebraically closed field, its cohomology will vanish in degree above twice its dimension, just like a complex variety. Like if you have a complex threefold, its singular cohomology will vanish above degree 6. If you take a variety over a non-algebraically closed field, its cohomology will not typically vanish in that degree. So for example, if you have a variety over a finite field, its cohomology will vanish over degree like twice the dimension plus 1. But in general, the top cohomology, the cohomology in twice the dimension plus 1, won't actually be 0. Okay. And in good situations, these things behave like you might expect. They're finitely generated, modules over these rings, like Z mod delta the n Z modules, for example. They have like Meyer-Vietoris sequences and excision sequences, and they're very special sequences, and this situation really looks a lot like singular cohomology. Okay, and Arvind asked about pi1, so we're also going to talk about that. So there's going to be a lot of related invariants, which are going to be very important. So for example, to x a scheme and x bar, here this is a geometric point of x. That just means a map in from spec of an algebraically closed field. We're going to associate a version of the fundamental group. And this is going to be a topological group, profinite group. Okay, and so we'll probably cover that in the 3rd or 4th lecture. And then in general, there are more invariants, which are kind of beyond the scope of this course. So for example, to a variety, a reasonably nice variety, you can associate higher homotopy groups. There's in fact a whole homotopy type, meaning like an actual like equivalence class of topological space, or slightly fancier object, associated to a variety. If there's interest in that and time at the very end of the course, maybe we could cover something about it, but my current plan is not to. Okay, and yeah, so that's the goal. We're basically trying to do some homotopy theory or get some homotopy theoretic invariants for varieties which are not over the complex numbers. Are there any questions about that? Okay, so I want to talk a little bit about the historical motivation and how this situation actually, in some sense, really differs from the complex numbers. So here's the first theorem I'm going to prove in the course. So this cohomology theory has to be kind of weird. Is weird. So here's a theorem of Serre, which I'm going to sketch the proof of. So there does not exist a cohomology theory for schemes over F of Q bar with the following properties. So one, it's functorial. So by cohomology theory, I just mean like a bunch of functors which associate to each variety over FQ bar a vector space we call HI. So they're functorial. It satisfies Kunith, and to E an elliptic curve, it's H1 of this thing is Q2. Okay, so the slogan of this theorem is that there's no cohomology theory with Q coefficients. All right. Does anyone have any idea of how one might prove this?
Can you see what the second condition means?
Oh yeah, so Kunith, it just means that if you take the product of two varieties, the cohomology is the tensor product. Let's say that's true if you have field coefficients.
And sorry, this is a dumb question. Do you know, can you say why we would want the third condition?
Yeah, so singular cohomology, you can stick in any commutative ring, right? And you get a cohomology theory, right? You can take cohomology with coefficients in that commutative ring, right? So what this is saying is that in the Etale world, you can't do that, and at least get the results you might expect. I mean, you could actually, if you wanted to, you could try to take Etale cohomology with coefficients, but it would not look like what you would expect. Like you expect H1 of an elliptic curve to be two-dimensional. So yeah, so that's what this is saying. Like somehow you need to do something interesting with the coefficients. Yeah, so does anyone have any idea of how you might get at this? So I'm just going to sketch the argument. So the idea is to take E to be a supersingular elliptic curve. Then the endomorphism algebra of E, tensored with Q, is a quaternion algebra. So this is just a fact. If you haven't seen this before, it's okay. And okay, so here's the key fact. So any algebra homomorphism from, so it's a here we have a non-split quaternion algebra. Let me call it R. So any algebra homomorphism from R to 2x2 matrices over Q. Well, they don't exist. There are no homomorphisms like this. Okay. Does anyone see where we're going? So the exercise, which you should try to do when you get home, is that functoriality plus Kunith implies that the action of the endomorphism algebra on E gives you a action of NE, meaning so the content here is that it's additive on H1 of E. Okay, and what is an action on a two-dimensional vector space? It's an algebra homomorphism to 2x2 matrices over Q. Okay, and that's a contradiction. Okay.
So I have a question.
Yeah, go ahead.
So what? So how about if it's a trivial homomorphism from? I mean, how about if the action is trivial?
So an algebra homomorphism has to send 1 to 1. So it can't be trivial.
Okay.
Yeah, that's a good question. Yeah, and I mean that already follows from functoriality though. Like the identity in this algebra is literally the identity on the elliptic curve, and functors have to send the identity to the identity. Yeah, so somehow the content here, which you have to unwind from Kunith, is that if you take the sum of two endomorphisms, they act via their sum on H1 of the elliptic curve. Yeah. Okay, and in fact, so in fact, here's also an exercise you should try to do is prove the same thing for QP coefficients, where here where here P divides the characteristic of your ground field. Okay, and the proof is more or less the same. You just have to know what quaternion algebras show up here. All right, so that's something you should try to do, and if you don't see what to do, you should come to office hours and ask about it. Okay, so what that tells us is that, I mean, I gave you this list of possible coefficients up here, like Z mod L to the NZ and ZL and QL, and it says we're at least forced to use some kind of funky coefficients like that. We can't use Z or Q. All right, so now I want to talk about the historical motivation. So, and also the motivation for the kind of the capstone of this course. So I want to explain what the Weil conjectures are. All right, so before I do that, are there any questions on what we've done so far? So, oh, Adil asks, functorial here means inverse images, Geiston, or both. I just mean there's they're functor. The HIs are functors. And Mencelos should read the Frobenius somewhere. So I sorry, that might have been a while ago. I think I missed maybe. Yeah. So sorry about that. Has your question been answered, Mencelos, or do you want me to ask it again? Okay, great. Okay, so now I want to tell you what Weil conjectures are and what the goal of this course is, namely to prove them. So, and I'm also going to try to motivate them a little bit. So suppose X is a variety over a finite field FQ. And again, that's a geometrically integral finite type separated FQ scheme. Maybe I'll write that out. Although very little of this will actually be relevant to the Weil conjectures. So then we associate a zeta function to X. So this is something that counts the rational points of X over finite extensions of FQ. And what's the definition? So it's this kind of complicated looking thing. We take the number of rational points of X over FQ to the N divided by N times T to the N. Okay, so this is kind of weird. Like I think the first time you see this, it looks a little funky. So maybe let me make some remarks. So first of all, why do we have this exponential business? So at least one reason is that if you take ddt log of the zeta function, this is a generating function, like a usual generating function for the number of rational points. So why is that? When you take the log, it gets rid of the exponential, and then when you take ddt, this n in the exponent here gets rid of this n in the denominator. Great. So the slogan you should keep in mind is that the locations of the zeros and poles of a meromorphic function and so far we don't actually know that this function is meromorphic, but we'll see that in a second. Of a meromorphic function control the growth rate of the coefficients of the Taylor series of its logarithmic derivative. Okay, so let me be explicit. So in this case, what that's saying is that the locations of the zeros and poles of the zeta function control the growth rate of the coefficients of its logarithmic derivative. Well, those coefficients are just the number of rational points. So that's saying that we've invented a function where the locations of its zeros and poles control the number of rational points of X over finite extensions of FQ. So an exercise you should try to do is make the slogan precise for rational functions, meaning ratios of two polynomials. And in fact, what you'll see in a second that's going to be the situation that matters for us. Okay, so the Weil conjectures are some conjectures about this polynomial. So conjecture one is that zeta x of t is a rational function. So it's a ratio of two polynomials. Okay. Conjecture two is that, well, it kind of deserves the name of a zeta function. So if it's a zeta function, it had better have a functional equation. So suppose x is smooth and proper of dimension n, So then let me write down the form of the functional equation. Then zeta x of q to the minus n, that's the dimension, t inverse, is equal to plus or minus q to the n e over 2. I'll say what capital E is in a second. T to the e times the usual zeta function. Okay, and what is E here? So E here is supposed to be the Euler characteristic. Okay, and that's something we don't know how to make sense of yet. And that's something that I don't think we know a priori yet how to define for varieties over finite fields. So maybe part of the conjectures are to make sense of that. Okay, so part 3 is that all roots and poles of zeta x of t of absolute value q to the I over 2. So here q is the size of fq, the field we're over, and here I is an integer. All right. So this is what people call the Riemann hypothesis. This is the functional equation. And this is supposed to be true without any assumptions on x. It's just an arbitrary variety. Okay, and then finally, returning to the case of x smooth and proper, so you can look at the number of roots and poles with absolute value q to the minus I over 2. Then this number is supposed to equal the ith Betti number of x f q bar. Okay, and again, we don't know yet what is meant by a Betti number, but at the very least, we can say this makes sense if x lifts to characteristic 0. So for example, suppose you took a variety defined by like a bunch of integer polynomial equations, which when you reduce it mod p gives you a smooth projective variety over fp. Then what you can do is look at the Betti numbers of the associated complex manifold and compare them to the number of roots. And Weil's conjecture was that those two numbers are the same. Okay, and we're actually gonna make sense of it in general. By taking kind of Betti numbers to be the dimensions of certain Etale cohomology groups. Okay, so historically, I mean, these conjectures are all theorems. So the proof was, one was by Dwork using kind of p-adic methods. So it was actually quite different from the eventual Etale cohomology proof. But in Etale cohomology, I mean, what is the content of this? So this is going to follow the sort of non-formal content will be the fact that the Etale cohomology groups are finite dimensional. So we'll see in a little bit that this is going to be related to the Lefschetz trace formula, but that's sort of more or less formal input, and not entirely, but largely. And then that combined with the finite dimensionality of the Etale cohomology groups is why this function is rational. But that's not Dwork's proof, but that's how maybe Grothendieck thought about it. Okay, so 2 was proven by Grothendieck. And this is going to follow from Poincare duality. Or some version of Poincare duality, at least. Okay. And then 3 and 4 are due to Deligne. And I think the first proof I want to give out the Weil conjectures will be quite close to Deligne's original proof, which I think is not always how these things are done, but I like the proof, and I think we'll learn a lot from it. All right. Great. So I want to spend, I guess we have 35 more minutes today. So maybe I'll pause and ask, are there any questions? And then after that, we'll talk a little bit about the Weil conjectures for curves, and then also an analog for compact complex varieties. Yeah, so any question is fine. You also, if you're visiting and not registered for the course, it's still fine for you to ask questions. All right, so I want to first of all explain the Euler product for these zeta functions, because I think it's kind of fun. So let's try to just play around with the zeta function a little bit. I think it's worth becoming friends with it. So first of all, what's the definition? It's just the exponential of this funny generating series. Right. Okay, and we can actually write that as a product over closed points of x. So I'm going to use x in bars this to denote closed points of x. And I claim that this is just equal to the sum of t to the degree x plus t to the 2 degree x over 2 plus, and so on, so t to the 3 degree x over 3, and so on and so forth. So does anyone see what this is? Yeah, so this is one of those times where the people registered in the course should consider unmuting and asking themselves why this might be happening. All right, let's think about it. So
the definition.
I'm sorry?
Oh, because it's a product. Okay, never mind.
Yeah, so when you take the product here, you kind of sum inside the exponentials, right? And then what's happening? Well, if you have a point of degree x, how many, so let's say the degree x is n, so how many fq to the n points does it contribute to your variety? In other words, I'm asking how many maps are there from spec of fq to the n to spec of fq to the n over spec of fq? So let's.
N.
I'm sorry?
N.
Yeah, n, exactly. It's the Kähler group of fq to the n over fq. So there's n. Okay, so that means we contribute n, but here we have a division by n. So that means we contribute, 1 to this sum. So that's why here we're dividing by 1. Okay, so it's an exercise to check that that's what's happening in general. Okay, so check this as an exercise if you haven't done it before. Okay, so that this interior sum has another description. Does anyone see a way to rewrite it? So my hint is it's related to the Taylor series of log.
Is it like log of 1 minus t to the degree x, or like t to the degree x minus 1?
I think it's minus that. So I think it's minus log of 1 minus 2 to the degree x. Exactly right. Okay, and so now you're taking x of log. So this is the same as log of something to the minus 1, right? So this is the product over x and x of 1 over 1 minus 2 to the degree x. Okay, so this is the Euler product. Okay, so that's a very simple description of the zeta function. So let's actually keep going a little bit. So this looks to me like the formula for a geometric series, right? So this is the product over x and x of 1 plus t to the degree x plus t to the 2 degree x, and so on, right? And what happens if we multiply out this product? So I claim that we can actually write this product as a sum. So what's the coefficient of t to the n? So I claim it's the following. I claim it's the number of Galois stable subsets of x fq to the n, or sorry, x fq bar of size n. Well, why is that? If you have a degree x point, it contributes a stable subset of size x, namely the fq to the n points of fq to the n, or respect fq to the n. And then if you take a bunch of Galois orbits like that, that's like multiplying out this product. Okay, and we can actually rewrite this one more time. So these are actually the points of some algebraic variety. So these are the points of sim n x over fq. So here, what is sim n x? It's x to the n divided by the action of the symmetric group. So why is that? Well, what's a point, a fq bar point of sim n x is just an n tuple of fq bar points of x without an ordering, right? And then asking them to be Galois stable is just the same as saying that they're an fq point, right? So that's why these two lines are the same. Okay, so this is another way to write the zeta function. All right, great. Cool. Are there any questions about that? So the reason I wanted to write it this way is that we can actually now do a proof of the first Weil conjecture for curves. So theorem. So suppose x is a smooth proper curve. Sorry about that. X is a smooth proper curve over fq. Then here's the theorem. The zeta function of x is rational. All right, so I want to actually use this description above to prove it. So those of you who have come to my office hours over the summer may have seen this proof, but I want to do it because I think it's geometric and it's very different from what we're going to do later. So I think it's kind of fun. But you'll see there's a relationship to what we do later. Are there any questions about what the goal is?
It is a dumb question, but just can you see where are we using the fact that it's a finite field, like above?
Oh, yeah. So well, for example, you want these numbers to be finite numbers, right? Like, I mean, you could certainly write down this formal product, but like usually, if you take the product over all, like if you take the product over all c points of a variety, that will be an uncountable product.
Right.
Yeah. So what we're using is that this product actually converges, or the sum actually, well, here you need these numbers to be finite, so you can write this down. Here you need the product to converge, and that you'll see requires that there's only finitely many points of each degree, which is in general false. And if you take a variety over Q, it might have finitely many Q points, but there will always be some degree where it has infinitely many points of that degree, unless it's a zero-dimensional variety. All right. So let's prove this. So can anyone tell me how to understand the geometry of, so we're going to use this formulation here. Can anyone tell me how to understand the geometry of sim n x where x is a curve? So I claim there's a map from sim n x to just the set of degree n line bundles on x. And what does this map do? It sends a divisor d, so here that a divisor is just an n tuple of points, to the line bundle O of d. Okay. Do you all agree with this?
Mm-hmm. Yep.
Yeah, great. So what are the fibers of this map? So what's the fiber over a line bundle O of d? So it's the set of divisors D, so D prime, so that O of D prime is isomorphic to O of D, right? Does that set have another name?
It's a linear system.
Yeah, it's a linear system. So another way of saying that is it's the projective space of the global sections of X of O of D. Okay, so what is the expected dimension of this space? So that the dimension of this projective space. So how do you compute the dimension of the space of line bundles the space of sections for a line bundle on a curve?
Use Riemann-Roch.
Yeah. So what's the formula?
So like genus plus degree minus 1.
Yeah, so it's genus plus the degree. Well, there's also a correction term, right? But sorry, so I think I think that's not quite right. So I think it's the degree of D, right? Maybe plus 1 minus G, but then there's a correction term.
Yeah, it's plus H0 of the
Well, so this is
canonical minus
H0, right?
Yeah, but then it's minus the dimension of H0 of the canonical minus D, or rather
Yeah, so
H1 of.
Right, that's H1.
Uh-huh.
Yeah, so the dimension of H1 of X of D. Okay, and then here, because we're taking the projective space, that subtracts 1 from the dimension, right? So let me erase that one. Okay. Great. So okay, we're going to need one more fact. So I claim that if D is big, if the degree of D is big, so in fact, bigger than 2g minus 2 is enough, then H1 of X of D is 0. Can anyone tell me why that's true?
I mean, that's the degree of a canonical bundle.
Yeah, so can you say a little bit more? So why does that imply H1 is 0?
Is it ample?
So the canonical of a curve is not always ample, right? What if it's
Sorry. Haha.
Or what if it was an elliptic curve? Yeah, so I think what you're getting at is that this is the degree of, this is the same as the dimension, so it's dual to H0 of X O of K minus D, right? And then this has negative degree. So if you have a line bundle of negative degree, it can't have sections, right? Great. So if you don't see why that's true, you should make sure you know why that's true. Okay, so what that says is that that the fibers. So what have we proven so far? So the fibers of this map are isomorphic to P of, I guess, sorry, N is the degree now, right? Of N minus G. If N is greater than 2G minus 2. All right. Okay, and so that's step 1. And then step 2, I'm gonna make a reduction. And you should, as an exercise, see why you can make this reduction. I'm gonna assume X of FQ is non-empty. So that implies that pick N is isomorphic as a set, so the set of degree N line bundles for all N. Can anyone tell me why why this holds? Why these sets are isomorphic, or in bijection to each other?
Just like the point, right?
Yeah, so you can take O of the point, that's the degree 1 line bundle, and then tensor with it, right? And that gives you an isomorphism between pick n and pick n plus 1. And well, why is it an isomorphism? Because you can tensor with the dual line bundle to go back. Great. Okay, so what this tells us, so what we've found, so that means that the number of points on sim n of x of fq is equal to the number of points on Pn minus G times the number of points on pick n. Well, that's the same as the number of points on pick naught. And this is true for all n bigger than 2g minus 2. Okay, so now we can rewrite the zeta function. So we get the zeta function of x is equal to some polynomial plus, so that's just the first 2g minus 2 terms, plus n bigger than 2g minus 2 of the number of points on sim n x. Well, we just figured out what that is. That's the number of points on pick naught. Times the number of points on Pn minus G. So how many points are there on Pn minus G? Yeah, so how many points are there on a projective space over FQ?
Q to the n minus G plus 1 divided by Q minus 1? Minus 1 somewhere?
Something like that. But so maybe the easiest way to remember it is it's just 1 plus Q squared all the way up to Q to the n, Q to the n minus G. Right? Okay, and now the exercise for you is to show that this is a rational function. Okay, and if like Makoto, you just use the formula for a geometric series, you'll see that this is not too hard. Okay, so we've gotten a more or less explicit formula for the zeta function, except for this mysterious polynomial in the beginning, and that's enough to show it's rational. I mean, if you take it's enough to show that this term on the right is rational, and if you take a rational function plus a polynomial, it's still a rational function. Okay, so now.
Daniel, I think you want your t to the n in that second term.
Oh yeah, sorry.
The sum up there.
Yeah, you're absolutely right. Great. Yeah, thank you. Sorry about that. Yeah. Okay. So now let me just say a word about the functional equation. So what is the functional equation in the case of curves? So it's the following. So the zeta x of q inverse t inverse is going to equal plus or minus, and you'll have to figure out what that is, q to the 2 minus 2g over 2 times t to the 2 minus 2g times zeta x of t. Okay, and the proof I'm also going to leave as an exercise. But does anyone have a guess as to where it comes from? If we use this formalism in terms of symmetric powers?
Does it come from Serre duality?
Yeah, it's going to come from Serre duality. So in other words, you're going to have to get enough control on this polynomial by writing it as you know, the counting sections to some line bundles to show that it has some kind of symmetry, and that symmetry is going to come from Serre duality. Okay, and this is of all the exercises I've done today, this is the one I want you to do the most. But so I really do encourage you to do this. And if you have trouble, you know, come to office hours, which I think will be this coming Wednesday. I'll send out an email about it. Yeah, you really should try this one. I mean, I think this is kind of a cool example where you, without much technology, can see somehow that some kind of duality, at least in this case, Serre duality, is what's giving you the functional equation. Okay, so that was a very non-cohomological argument. So we're going to do the Riemann hypothesis for curves later in the course, and then the Riemann hypothesis for all varieties. But now I want to kind of sketch at least what the idea is of the proof of rationality of the zeta function with Etale cohomology. So now here's the theorem, and this is the theorem of Dwork. So suppose x over fq is any variety, then the zeta function is a rational function. And I think the idea of the proof I'm going to sketch now, which we'll make precise over the course of this semester, it was already known to Weil when he made the conjecture. So if you look at his original paper, there's some hints of it, although he doesn't really make it explicit. But the idea is to use some kind of Lefschetz fixed point formula. So this is a sketch of the proof that's due to Grothendieck, not the proof due to Dwork. So the idea is that we're going to take the Frobenius map from x to x. Okay, and I'm being intentionally vague about which Frobenius map. There's a lot of Frobenius maps floating around. There's like a relative Frobenius and an absolute Frobenius and a geometric and arithmetic Frobenius, and I won't be precise yet. But the idea is to realize the rational points of x as the fixed points of Frobenius on x fq bar. And then in general, the points, the fq to the n points are the fixed points of Frobenius to the n. And then we're going to use the Lefschetz fixed point formula. Which later on is going to say the following. It'll say the number of rational points of x over fq to the n is equal to the sum from I equals 0 to twice the dimension of x. So those are the degrees in which x is supposed to have cohomology of -1 to the I times the trace of Frobenius to the n on something that I haven't really alluded to, the compactly supported cohomology of x over fq bar with QL coefficients. So a lot of this course is going to be devoted to making sense of what these words mean. And here we're going to have to assume that L is not equal to the characteristic of fq. Okay, and then once we have this formula, what's the fundamental lemma? So the lemma is that if V is a finite dimensional vector space, and F from V to V is a linear map, then this following formula, exp of sum of the trace of the powers of n for n times t to the n is rational. Okay, so hopefully this formula looks like the zeta function if you rewrite it in terms of this Lefschetz fixed point formula. So are there any questions about why the lemma should imply the theorem? So the point is that you just plug this formula into the definition of the zeta function, and then you'll see you get a product or an alternating product of a bunch of things like this. And then if you have an alternating product of rational functions, it's rational. All right, are there any questions about that?
Sorry, what do you mean by an alternating product?
Oh, just a product times a product of 1 over something times a product times a thing times 1 over something times a thing times 1 over something. So here, the point is this: when you plug them into the exp, this sum of -1 to the I becomes a product of like exp of negative something is 1 over exp of that thing, right? Does that make sense, Arvind?
Yeah, thanks.
Yeah. Okay. So I mean, the proof of the lemma is I mean, I'll just say a word about it because it's not hard. So it suffices to treat the case where the dimension of V is 1, because you can just write this as a sum of powers of eigenvalues. And then, well, then you have a scalar matrix. So then you have exp of sum of alpha to the n over n t to the n. Well, this is just exp of negative log of 1 minus alpha t, which is 1 over 1 minus alpha t, which is rational. Okay, so what was the key input? So we've now proven rationality of zeta functions subject to two things. So one, well, we need this Lefschetz fixed point formula that I wrote up here, and we so far we don't even know what these words mean or what these symbols mean. But two, I mean, this lemma really relies on the finite dimensionality of these vector spaces, or also these vector spaces. So we need finite dimensionality of Etale cohomology groups. Okay, so that's the real geometric input. Okay, so as an exercise, so like before with the case of curves, you should try to figure out how Poincare duality should give the functional equation. Okay, and my hint is just to try this lemma on a vector space which has a bilinear form, and where this f scales the bilinear form. So it preserves it up to scalar. Okay, so we only have 7 minutes left, so I think I'm not going to have time to do the Kähler analog of the Riemann hypothesis today, but maybe I'll state it, and then we can talk about some questions about it. So the final kind of motivation I want to give you for the rest of the course is this theorem of Serre. So suppose X is a smooth projective variety over the complex numbers. So suppose H in just the singular cohomology of the complex points of X is a hyperplane class. So you can think of this as like the cohomology class corresponding to the intersection of it with a generic hyperplane, or if you want, the first Chern class of an ample line bundle. Now suppose F, here this is all set up here. So suppose F from X to X is an endomorphism such that the pullback of this hyperplane class is equal to Q times the hyperplane class, where here Q is some positive integer. Okay, then I'm going to make the following definition. So this is the Lefschetz number of X. It's just what you get from the Lefschetz fixed point formula. So it's the alternating sum of -1 to the I times the trace of F star to the N, acting on the ith cohomology of X with, say, Q coefficients. And now from this we can define a zeta function. Sorry, I'm defining so much stuff. So this is going to be the exponential of the sum from n equals 1 to infinity of these Lefschetz numbers times t to the n. Okay, then the theorem is that the zeta function satisfies the Riemann hypothesis. And I'll be precise about what I mean by that. So I mean all the zeros and poles are half integer powers of Q, where it's this Q. So an equivalent formulation, which is what I'll actually prove next time, is that the eigenvalues of F acting on HI, well, maybe I'll put a C here, all have absolute value, Q to the I over 2. Okay, so the proof of this theorem in the end is going to look quite different from the proof, Deline's proof of the Riemann hypothesis, but it still, I think, really motivates it and also motivates a lot of conjectures in kind of the theory of, in cycle theory, like the standard conjectures. Okay, so I'll prove that at the beginning of next time, and then, so next time, sorry, we went a little bit over, or we didn't cover everything I wanted to cover. So next time I'll prove this, and then I'll start to really get into the course material. So we're gonna review what Etale morphisms are. And then if we have time, talk about the Etale site, and what it means to have a site. So before next time, please just review the definition of an Etale morphism. And I'd suggest looking at the relevant chapter in Milne or the Stacks project or Hartshorn. Any of those sources are going to be fine. All right, so we have, I think, 3 minutes left. Are there any questions?
You gonna post the export of the notebook to Discord or something?
Oh yeah, I can post this, sure, and I'll also post the recording.
Awesome.
Any other questions? All right. Well, if not, thank you all for coming. I'll see you next next Tuesday. And yeah, I'll keep you posted on what the developments are with the in-person aspects of the class and so on. Yeah. Thank you all for coming. And I'll stick around for a couple minutes in case anyone has any other questions.